In today's class and video, we are going to look at plots of enzyme kinetics. And we are going to use these plots to determine the Michaelis-Menten constant for the catalysis of p-nitrophenol phosphate by maize germ acid phosphatase. So let's start our introduction by looking at Michaelis-Menten plot. So first of all, what we have to note is that Michaelis-Menten plot is a graph that shows the relationship between the concentration of a substrate and the rate of the enzyme reaction. The plot is used to determine enzyme parameters such as the Michaelis-Menten constant and the maximum reaction rate. So now let us look at the characteristics of this graph. So let us start by looking at the axis. So what we have to note is that the reaction rate is on the y-axis as seen over here, and the substrate concentration is on the s-axis. And also, the plot curve represents the Michaelis-Menten equation, which describes the kinetics of enzyme reactions. And the shape of this plot also provides insight into the enzyme functions, the enzyme substrate affinity, and the saturation point for our substrate. So now let's look at the Michaelis-Menten equation from the plot. So from the plot, we have our equation to be given as V naught equals V maximum times the substrate concentration divided by Km plus the substrate concentration. So our V naught is the initial reaction velocity. Our V maximum, which is seen over here, is the maximum reaction velocity. Our Km happens to be the Michaelis constant, and it is the substrate concentration at which the maximum reaction velocity is halved. So as you can see over here, so this is half the maximum reaction velocity, and this is our substrate concentration, which is normally represented on the s-axis as seen over here. So now let's look at another important plot, Lineweaver-Burk plots. So first of all, what we have to notice is that the Lineweaver-Burk plot is a graphical representation of enzyme kinetics. So the s-axis is the reciprocal of the substrate concentration, and it is normally given as 1 over the substrate concentration, and the y-axis is the reciprocal of the reaction velocity, or normally written as 1 over v. In this way, the Lineweaver-Burk plot is often also called a double reciprocal plot. So what we have to note is that instead of using the Michaelis-Menten equation, we can take the reciprocal of both sides to obtain the double reciprocal plot. So now let us see how to do that. So this is our Michaelis-Menten equation given as V naught equals V maximum times the substrate concentration, not divided by the Km plus the substrate concentration. Now, so if we are to take the reciprocal of this equation, we are going to get 1 over V naught to be equal to our Km plus the substrate concentration, all divided by V maximum times the substrate concentration over here. So we can again expand this equation to get something like 1 over V to be equal to Km all divided by V maximum times the substrate concentration plus our substrate concentration divided by V maximum times the substrate concentration. So if we are to cancel out, so we can see that we will end up getting an equation to be equal to 1 over V to be equal to Km divided by the V maximum times 1 over the substrate concentration over here plus 1 over V maximum. And if you are to equate this equation to the equation of the line, you can see that, which is giving us y equals ms plus c. You can see that our y will be giving us 1 over v, and our slope will be giving us km over the v maximum. Our s will be 1 over the substrate concentration, and our intercept, which is on the y-axis, will be giving us 1 over v maximum. So this is the equation of the Lineweaver-Beck plot. So now, as explained earlier, we can say that this is our y, which is giving us 1 over v over here, and the slope is also giving us km over the v maximum from the equation, and we have our s giving us 1 over the substrate concentration from the equation, and also on the y-intercept we have 1 over v maximum, and we can also see that the intercept on the s-axis will be giving us negative 1 over km. And now let us look at the importance of this Lineweaver-Beck plot. 1, it's used to determine the maximum velocity of the reaction. 2, it's used to determine the slope of the reaction. And 3, it is used to determine the Michaelis-Menten constant of the reaction. And 4, it is used to differentiate between the types of reversible inhibitors. So now let us look at our test protocols. And we are going to start by looking at the materials that we are going to use to perform this experiment. So we have acid phosphatase as our enzyme, 0.025 molar p-nitrophenol phosphate of pH 4.8 as the artificial substrate. We have our 0.1 molar citrate buffer of pH 4.8. We also have water bath set at 37 degrees Celsius, 0.1 molar sodium hydroxide, and a UVV spectrophotometer set at 405 nanometer. So these are the various materials that we are going to use in performing this experiment. So now let's look at the test method. So the first method is a substrate buffer preparation. And to prepare our substrate buffer, we prepare a series of 5 test tubes. So these are the 5 test tubes you can see over here, containing 0.05 mils of our artificial substrate, 0.1 mil of our artificial substrate, 0.2 mils of our artificial substrate, 0.5 mil of our artificial substrate, and 1.0 mils of our artificial substrate. So once we are done with this, to each test tube, we add 2 mils of our 0.1 molar citrate buffer of pH 4.8. So as you can see over here, so to this test tube, we are adding 2 mils of our 0.1 citrate buffer, the same for this, the same for this, same for this, and same for this as well. So once we are done with that, we top up to a volume of 4.5 mils with distilled water. So as you can see, so this is the first test tube. We add 2.45 mils of distilled water to it to get a final volume of 4.5 mils. For the second test tube, we add 2.4 mils of distilled water to it to get a final volume of 4.5 mils. To test tube 3, we add 2.3 mils of distilled water to it to get a final volume of 4.5. To test tube 4, we add 2.0 mils of distilled water to it to get a final volume of 4.5. And to test tube 5, we add 1.5 mils of distilled water to it to get a final volume of 4.5. So the next is the enzyme dilution. So we are going to do 1 in 10, 1 in 100, and 1 in 1000 dilution in a final volume of 5 ml. So to do this, we prepare 5 ml of the following dilution of the stock acid phosphatase. So to prepare our 1 in 10 dilution, we pick from our stock acid phosphatase 0.5 mils and add to a test tube containing 4.5 mils of distilled water to prepare our 1 in 10 dilution. For the 1 in 100 dilution, we pick from the 1 in 10 dilution 0.5 ml and add to a different test tube containing 4.5 ml of distilled water. And to prepare our 1 in 1000 dilution, we pick from our 1 in 100 dilution 0.5 ml and add to a test tube containing 4.5 ml of distilled water. So the next method is the equilibration of our diluted enzyme and our substrate buffers at 37 degrees Celsius for 5 minutes. So as we can see, this is our water bath set at 37 degrees Celsius, and we equilibrate the diluted enzymes and the substrate buffers by dipping them into the water bath set at 37 degrees Celsius for 5 minutes. And what we have to note is that the diluted enzyme here represents our 1 in 10, 1 in 100, and our 1 in 1000 dilution. And the substrate buffer also here we represent the 5 different substrate buffers that we prepared. So the next is to perform a substrate enzyme reaction, or in other words, is to perform our reaction mixture. So what we do is that after the 5 minutes of incubation, we add 0.5 ml of the equilibrated enzyme. So this is the equilibrated enzyme to the 4.5 ml substrate buffer in the water bath. And what we have to note is that once we add the equilibrated enzyme to the substrate buffer, it now becomes our reaction mixture. So we mix and immediately remove 1 ml of the reaction mixture and add to a different test tube containing 5 mils of 0.1 molar sodium hydroxide, and we take this as our zero time because it is assumed that there will be no reactions, since right after adding the enzyme to the substrate buffer, we mix and immediately took 1 mil and add to a different test tube containing our 0.1 molar sodium hydroxide. And what we also have to note here is that the reaction mixture here represents each of the 5 reaction mixtures that we have prepared, and the 5 mils of the 0.1 molar here represent each of the 5 test tubes containing 0.1 molar sodium hydroxide. So the stopped reaction over here will be used as our blank against the various times of incubation. So that is the 10 minutes and the 20 minutes that we will be doing further. So we repeat this step at 10 minutes and 20 minutes interval for each tube. So what it means is that after adding our equilibrated enzyme to our substrate buffer in the water bath, we allow it to stand in the water bath at 10 minutes. So after 10 minutes of the incubation, we pick 1 ml of the equilibrated sample and add to 5 ml of 0.1 molar sodium hydroxide contained in a different test tube. And also after 20 minutes of incubation in the water bath, we also pick 1 ml of the reaction mixture and add to a different test tube containing 5 ml of 0.1 molar sodium hydroxide to stop the reaction. And once again, the reaction mixture here represents each of the 5 reaction mixtures, and the test tube here represents each of the 5 test tubes containing 5 ml of 0.1 molar. So this is the sample that we are going to measure its absorbance at 405 nanometer against the blank at 0 minutes. So this is just an assumed table of result, and I'm just using the 1 in 10 dilution. So if you look at the table, we have the volume of p-nitrophenol phosphate added to each of the test tubes. So we have 0.05, 0.1, 0.2, 0.5, and 1.0, and this happens to be the volume of buffer, that is the citrate buffer that we added. So we can see we added 2 ml to each of the test tube. This is the volume of water that we added. So we had 2.45 to test tube 1, 2.4 to test tube 2, 2.3 to test tube 3, 2.0 to test tube 4, and 1.50 to test tube 5. And these are the various absorbance values that we had for the 10 minutes of incubation and 20 minutes of incubation. Remember that for the 0 minutes, we use that as a blank against the incubation at 10 minutes and 20 minutes. So the absorbance value at 10 minutes for our first test tube is 0.073, 20 minutes is 0.174. For the second test tube will be 0.076, and 20 minutes 0.195. For the tube containing the third tube is 0.085 for 10 minutes, and 20 minutes we have 0.3. So at 10 minutes the absorbance value for the fourth test tube is 0.253, and at 20 minutes we have 0.414. So for the last test tube at 10 minutes we have 0.332, and at 20 minutes we have 0.532. Let us look at the determination of the p-nitrophenol hydrolyzed from the artificial substrate p-nitrophenol phosphate by our enzyme acid phosphatase at 10 minutes of incubation from the p-nitrophenol calibration curve. So this is our p-nitrophenol calibration curve with the equation of the line giving us y equals 6.7318s. So where y happens to be the absorbance value, the 6.7318 happens to be the slope, and the s happens to be the moles of p-nitrophenol formed or hydrolyzed. So I'll do this calculation by just looking at one example. So I'm going to do for the first test tube containing the 0.05 mils of the artificial substrate. Now, so from the equation over here, to calculate the moles of the p-nitrophenol formed or hydrolyzed by our enzyme from the artificial substrate, we make S the subject. So the moles of p-nitrophenol from which is S is giving us S equals Y divided by 6.7318 over here. And as mentioned earlier, the Y happens to be the absorbance value obtained at the 10 minutes of after the 10 minutes of incubation. So if we should come to our table and taking the first test tube, we can see that the absorbance obtained is 0.073 over here. So if you are to substitute this value into the equation S equals Y divided by 6.7318, so where Y is the 0.073, we will get 0.0108 micromole. But what we also have to note is that the enzyme used was diluted. So we did 1 in 10 dilution, 1 in 100, and 1 in 1000 dilution. But the example that I'm showing over here is for the 1 in 10 dilution. So what it means is that to obtain the actual moles of p-nitrophenol hydrolyzed from the artificial substrate by our enzyme, we will have to multiply the moles obtained over here times the dilution factor, which is 10. So to do this, we will get 10 times this, so which will give us 0.108 micromole. And if you are to do the same thing for the second test tube, you will get this as the actual moles of the p-nitrophenol hydrolyzed. For the third test tube, we will get this as the actual moles of the p-nitrophenol hydrolyzed. The fourth test tube, we will get this, and the fifth test tube, we will get this. So now let us calculate the reaction velocity. So what we have to note is that the reaction velocity is given as the moles of the p-nitrophenol formed divided by the moles of or the volume of the reaction mixture used and the time of incubation at each substrate concentration. So let us just go through the calculations over here. So if you are to take the first test tube, which is test tube 1, So we know that the moles of p nitrophenol formed is given as 0.108 over here, divided by the volume of the reaction mixture, which is 5 ml, times the time of incubation, which is 10 minutes. So if you have to solve this, we will get 2.16 times 10 to the power negative 3 micromoles per ml per minute. So for the second test tube also, we know the moles hydrolyzed to be 0.113 micromoles, divided by the volume of the reaction mixture times the 10 minutes of for incubation. We also get this. So for the third test tube, we are getting this. For the fourth test tube, we are getting this, and for the fifth test tube, we are getting this. And one thing that we also have to notice that to plot a Lineweaver-Beck plot, we always plot the inverse of the reaction velocity, which is given as 1 over the Vm, against the inverse of the substrate concentration, which is also given as 1 over the substrate concentration. So what it means is that we have to determine the 1 over Vm over here. So to do this, we divide, so we just make it 1 divided by the reaction velocity here, we will get 463. 1 divided by this, we will get 442.5, and 1 divided by this, we will get this, and 1 divided by this, we also get this, and 1 divided by this, we also get this. So this is just a table showing the moles of p nitrophenol hydrolyzed and the reaction velocity for each of the reaction, and the inverse, or the 1 over v of each of the reaction velocity. So now let's move on and look at the substrate concentration. So first of all, we are going to use the equation given as C1 equals C2, C1 V1 equals C2 V2. So in this equation, we will make C2 the subject, and making C2 the subject, we are going to get C1 V1 all divided by V2. And what I want us to note here is that the C over here happens to be our substrate concentration. So the C1 happens to be the initial substrate concentration, and the C2 happens to be the final substrate concentration. So we are using this table as a guide to do our calculation. So first of all, what you have to note is that for each of the test tube, we added different volumes of our artificial substrate. So for the first test tube, we added the 0.05. So that means our C1 here, our V1 here is 0.05. For the test tube 2, we added 0.10, and test tube 3 0.20, test tube 4 0.50, and test tube 5 1.00 over here. So these are our C1s, our V1's values over here for each of the test tube, and the volume and the final volume of our substrate buffer is 4.5. So what it means is that our V2 obviously will be 4.5 mils, and the initial concentration of our of the substrate used in preparing the substrate buffer is 0.025 molar over here. So this one also run through. So now let's begin to look at how the calculation will be done. So don't forget I said the C2 over here happens to be the final substrate concentration. So let us do for the first test tube. So test tube 1, we have our substrate, the final substrate concentration in the substrate buffer to be given as 0.025, and this is our C1 times the 0.05, which is the mils of the p nitrophenol phosphate added, divided by V2, which is the final volume. So if you have to substitute this, you get 2.78 times 10 to the power negative 4. So for the second test tube, we will get our substrate concentration to be this. For the third test tube, we'll get our substrate concentration to be this. The fourth test tube, you'll get our substrate concentration to be this. And the fifth test tube, our substrate concentration to be this. And once again, we have to know that to plot our graph or our plot, which happens to be the Michaelis-Menten plot, we always plot our 1 over Vm against the inverse of the substrate concentration, giving us 1 over the substrate concentration. So what it means is that we will now have to calculate for the 1 over the substrate concentration. And to do this, so it will be 1 divided by this, which will give us this, and 1 divided by this will also give us this. 1 divided by the substrate concentration here will give us this. 1 divided by this will give us this, and 1 divided by this will also give us this. So this is our table showing the values that we are going to plot to obtain the Michaelis-Menten plot. So for the first test tube, we have our the inverse of the substrate, which is 1 over the substrate concentration, to be 3597.1, and our 1 over v given as this. So for test tube 2, we have this for the 1 over the substrate concentration, and this for the 1 over the reaction velocity, and this also we had this and this, and for the test tube 4, these are the values that we had, and for the test tube 5, these are the values that we had. So we will plot this against this. So if you are to plot this against this will be the nature of graph that we are going to get. So let's now calculate our V maximum and Km value for our PMPP in the enzymatic reaction. And to do this, we will have to use the equation of the line for the plot over here, which is giving us y equals 0.0938s plus 187.75, and equate this equation over here to the Michaelis-Menten equation, which is also given as 1 over v equals Km divided by v maximum times 1 over the substrate concentration plus 1 over v maximum. And if you are to equate the equation of the line to this equation, we can see that our y will be 1 over v, the slope will be Km over the v maximum, and the intercept, which is 187.75, will be equal to 1 over the v maximum. So if you are to equate 1 over the v maximum to the intercept over here, 187.75, and we make v maximum the subject, so we will get v maximum to be equal to 1 divided by the intercept, which is 187.75 over the n. If we are to solve for this, we will get our v maximum to be 5.326 times 10 exponent negative 3 units per mole. So this is our v maximum for our PNPP in the enzymatic reaction. And also, if you want to calculate for our Km, we know that from this equation, Km over the v maximum is equal to our slope over here, which is 0.0938 over here. And if you are to make Km the subject, if you are to equate Km over v maximum to the value over here, we will see that our Km will be equal to the slope times our v maximum. So this will be equal to our slope, which is 0.0938 times our v maximum that we obtain over here. And if we are to calculate for this, we will get our Km to be 4.996 times 10 exponent 4 micromoles.